Hey developers out there, this is Stefan from Be a Python Dev, here to talk about solving the Fibonacci problem in Python and using dynamic programming to make it faster, easier, more reliable, all that fun stuff. This same general solution can apply to pretty much all the coding languages. The syntax is going to be a little bit different, but for starters, the Fibonacci series is just a series of numbers where the next number equals the sum of the previous two. So you'd have something like this, then this, and then it gets pretty bigger as you keep going up. And the fourth number in this series, so if n were to equal to 4, you'd return 2. If n were to equal to 5, you'd return 3, and so on, right? Right. I think that's how that goes. And you can solve this recursively by just taking the sums of the previous calls, like starting with the bottom up. To get the fourth value, all you need to do is take the third value and the second value and add those. But to get the third value, you need to get the second and the first, and so on and so on. So that ends up being like a bottom-up recursive problem where you have fib n equals fib n minus 1 plus fib n minus 2. So if we were to pass in 3, we just get fib n by calling the function again with fib 2 and calling the function again with fib 1. And then each one of these would call down and so on and so on. And you'd eventually have a lot of function calls on the stack, potentially leading to a lot of memory usage. Your recursive call also needs a base case, which will be something which will tell the function to stop if we try to call like fib -1, because we don't have -1 numbers in our series. So if n is less than or equal to 1, return n. And then, is it useful to you guys if I print values? So I'll just print n here so you can see how many times it's getting called down into. And then eventually you just return this fib n value. And this should be all you need. So we'll run the code, and fib is not defined. Why is that? Because it's in a class, so it needs to be self.fib. For some reason I thought it was just a function. Okay, so your input 5, and you can see when we're calling 5, we end up calculating 4 and 3. And then when we calculate 3, we go down to 2 and 1, and then 0. And then you can see our calls kind of recurse up. And just for the fifth value, we end up calling this function like what? 1, 2, 3, 4, 5, 6, 7, 8, over 10 times. Obviously, if n is very large, that's a lot of function calls, and your program's going to run very slow. So to make this even faster, we can use a thing called dynamic programming to end up saving space and optimizing this by using an iterative bottom-up solution. So we know that to get the next value in this series, you just sum those two values, right? Let me do this somewhere where it's a little more clear. So you sum those two values. To get this next number, you sum this value. And I did that wrong. And then you go 3, and then you kind of like move up the line. And if we do it this way, we end up having an O(n) problem. The only thing you need to be aware of in this kind of problem is how do we populate our values? You're going to need the previous value and the current value. So you're going to need two spots in your memory. So O2, which simplifies to being O1 memory space. So we'll have xy equals 0, 1. Nice little thing about Python is you can pack it this way. And then we can do our iterative loop. So for n in range, we're going to start at 2, and we're going to end at n plus 1. because the 0 value counts in the array, I guess, right? So this the the first value for n would actually be 1. No, it starts at 0. They start counting at 0. So the 0 value in the Fibonacci series is 0. The second value is 1. The third value is 2. Right? Yes. Sorry about that. Okay. So to do this, our fib value is going to be our fib value just equals x plus y. And then we shift these. So this equals y fib. And then we just return fib n. I believe this is all you end up needing now. Fib not defined because it actually needs to be fib n. Okay, so when the input is 5, let me just add this to a comment. 1, 1, 1, 2, 3, 5, 8. So we passed in 5 for our input. So this is the 0 number, the 1, the 2, the 3, the 4, the 5. So if we change our test case to pass in 6, then it should end up being 8. 8. And you can see that this runs a lot faster. And if we were to put like a print n, we're literally just printing n in this loop range. And I did something weird. I just ended up dragging that. So this is one way to convert a top-down recursive solution into a bottom-up dynamic programming solution, where you define your memory space that you're going to use to store the dynamic problems, and then you populate that as you change the problem and iterate through it, updating the dynamic memory space as you go through. So the next thing we can do with this is use it for the Fibonacci series, which is actually a little more complicated. And if you were going to do this with recursion, you would end up with a function that looks something like return self.Fibonacci n-2 and plus n-1 plus n-3. Yeah. And that ends up being kind of complicated. So you can simplify this by creating a dynamic programming memory array. We'll just call this dp equals 0, 1, 1. And kind of similar, going bottom up, we'll update this, we'll shift our values to the left, and we'll add the new Fibonacci value to the right. So the next value for this would be 2, and then we end up like doing something like this. And then the next value again would be 4, and then we end up, taking off the first value, and then so on as we keep going up and up. So we end up with 7, and then 13, etc. So we'll initialize this to 0, 1, 1. Then after initializing this, if n is less than or equal to 2, we'll just return dpn. And then else, we'll use the same kind of bottom-up iteration range for I in range n, starting at 3, starting at 2. I think it's starting at 2. Trib n equals the sum of the values in our array. And then what we can do to update our array here is we can pop the front value and then append trib n. And then we just return trib n. So we'll go ahead and run this. Your input 4, output 7, expected, wrong. So I think for I in range actually starts at 3. Because the 2 value is solved in the base case. So we start at 3 and then go out to n plus 1. We'll go ahead and submit this. Shows success here over in the corner to show that this dynamic programming approach works for the Fibonacci. Instead of having n cubed calls on the stack for all of the recursive calls to the Fibonacci function. You can simplify this even further by, instead of doing list manipulation, since a Python list is slightly more expensive than just using like 3 variables, you can initialize x equals 0, y equals 1, and z equals 1. And with Python, you can actually do this even cleaner by just initializing these in a packed tuple like this. And then if n is less than or equal to 2, return 1 if n. So if n is greater than 0, we're going to return 1, else n. So if n is 0, it's going to hit this else condition and just return n. And then here, I think it's just the same thing, x plus y plus z. And then you can clean up the logic here by just doing xyz equals yz trib n. And then I believe if we return trib n, it should end up being the same thing. The only thing I'm slightly forgetting is if this return 1 if n else n code actually works. So we'll update our test case manually. We'll add a 0 in here. Okay. So yeah, 0 does not evaluate to if n. So if n equals 0, then it is then it's not true. And then we'll do test case equals 2, correct input, and then we'll go ahead and submit this. You can see that this runtime, 61 milliseconds, faster than 5.69%. I think that's just being random. Not sure what would be faster than this, but we can look into that. And then memory usage, not bad compared to our previous one. And that's how you solve the Fibonacci problem and the Fibonacci problem in Python, using a recursive solution and then simplifying it to a dynamic programming solution with a bottom-up iterative approach. Thanks for watching. See ya. Bye.